Let's now look at an application of Laplace transform from control theory. The particular application we're going to look at is called a servo mechanism that models an automatic pilot, typically what you might find in a craft such as a boat or an airplane. The basic model is this, that you have a desired direction given as a function g of t, but there's a true direction that you're currently achieving, which is given by a function y of t on the steering mechanism. And the goal is to provide the feedback with what's really happening in the true direction back to the system so it can correct to achieve the desired direction. That correction is achieved by solving this equation, which is basically a form of Newton's second law. I times y double prime equals negative k, which is at a constant, k is a constant, times e. I is the moment of inertia. Y, of course, again, is the true direction. And this e is known as the deviation function, or it's the difference between your true direction and your desired direction. Again, it's a function of time. So again, y of t is the true direction, or angle, you could say, of the craft at time t. And g of t is the desired direction. So essentially, this mechanism applies a torque to the steering control shaft so that the plane or the boat will follow the prescribed course, as indicated by g of t. So the problem we want to look at is specified this way. Given this servo mechanism, can we determine the deviation as a function of time in the case that the steering shaft is initially at rest in the zero direction and the desired direction is given as a linear function just a times t, where a is some constant. So again, the g of t is just some constant a times t, as t varies, and we're interested in finding out a expression, mind you, of what this deviation function would have to be. Okay? All right. So what we're going to do is we're just going to start off by looking at how to solve the problem as an IVP. So what we'll do is we'll go ahead and write down what the IVP would look like for this particular problem. All right. So with Newton's second law, we have I here times y double prime, function of t, equals minus k, that constant, times the deviation function, which we're trying to find. The initial conditions, what we were given, steering shaft's initially at rest, so y of z equals equal to 0, as well as the derivative at 0. So those are our initial conditions. Again, I here is the moment of inertia. Of the steering shaft. K is a proportionality constant. So those are just real numbers. Okay. So again, for this particular problem, E has a certain form. E of t, right, is the true direction minus the deviation, which in this case is just y of t minus this constant a times t. Okay? Right? So we want to solve this particularly for e of t as opposed to y of t, but we'll set it up as if we were going to solve for y of t. So what we'll have to do initially is take the Laplace transform. So we're going to take the Laplace transform of both sides. And keeping in mind that we do have some constants involved here. So what that could mean is we could pull the I out, and of course the Laplace transform of that constant, we know that the Laplace transform is a linear operator, so we can write this as I times the Laplace transform of the second derivative of t, which is a function of s, so we'll take our notice that we are switching to the s domain. And this will be equal to minus k times the Laplace transform of our e of t, our deviation function, which of course is also a function of s. Right? Keep it in mind, we have properties, your table of properties for the Laplace transform, so we know how to rewrite the Laplace transform of the second derivative using the Laplace transform of y. So this will be I times the s squared term, right? we'll do capital Y of S to represent the Laplace transform, minus S times little y of 0, minus y prime of 0. And we'll set this equal to minus k times E of S. Well, now we'll make some definitions here. Okay. So the definitions that we're going to be using is that the capital Y of S is the Laplace transform of Y as a function of S, and that the capital E of S is the Laplace transform of the deviation function, which is a function of S. But keep in mind we have these nice initial conditions that we're going to basically wipe out these two terms here. They're both 0. So what we simply have is that S squared, let's write it this way, S squared times I, Laplace transform of S, Y of S, the Laplace transform of little y, I should say, is equal to minus k times E of S. Okay. Now that's true for regardless of what the deviation function is, but now we have a particular case, right? We know something about what the deviation function is. So E of S, this case, is the Laplace transform, right, of y of t minus the deviation, but the deviation now is at. And this is a function of S. Okay. So again, the Laplace transform is a linear operator. This is the same thing as the Laplace transform of y of t. It's a function of S. Right? Minus a times the Laplace transform of t as a function of S. So again, this is E of S. Again, that's the definition we just made. So in this case, E of S is just the Laplace transform written this way, capital Y of S, minus a times what? Go to your table, right? Laplace transform of t should be 1 over s squared, so this will be divided by s squared. Okay. Now, if we just rearrange this, if we solve this for y of s, what that would say is that y of s, the Laplace transform of little y, is nothing but E of S, the Laplace transform of your deviation function, plus a over s squared. Just solving for it, okay? So now what I want to do is take this information that we'll take, and what we want to do now is go back to this equation up here and replace y of s with this E of s expression plus a over s squared, and totally get an equation in the Laplace transform of E of t. That's what we wanted to solve for anyway, that deviation function. So if you do that, take this expression right here for y of s, plug it up here, then what you're going to end up with is s squared times the moment of inertia, E of s, plus that constant I times the moment of inertia is equal to minus k E of s. Okay? Again, that's the Laplace transform of your deviation function. So if we solve now for E of s, you would get minus a over times the moment of inertia divided by s squared times the moment of inertia I plus that proportionality constant k. Trying to get this in a form for which we can do the inverse transform, the inverse Laplace transform, you can show this would be the same thing as minus a over the square root of that little k divided by the moment of inertia times, in the numerator, the square root of that constant k divided by the moment of inertia over s squared plus k over I. Noticing that this term is really the square root of k over I quantity squared. Therefore, you can see from the Laplace transform table, this looks almost perfectly the sine, like the sine function. Okay. So let's look on another sheet of paper. Let's take this and then look at what we have here. What we've got is that we have E of s is this minus a over the square root of the proportionality constant divided by the moment inertia times the square root k over I over s squared plus k over I. So E of t then, which is the inverse Laplace transform of the capital E of s, which is a function of t, mapping it back to the t domain. The constant remains outside. Remember, the inverse Laplacian transform is a linear operator also, so we'll pull out that a term divided by the proportionally constant divided by the moment inertia. Then we see this form perfectly matches the sine form, but it's the sine of, take the inverse Laplace transform, square root of k over I times t. So therefore, the deviation function we were interested in solving for the servo mechanism is given by minus a quantity over the square root of k divided by I times the sine of the square root of k over I, that same term, t. This deviation function explains how to correct the servo mechanism when the true direction is not matching the desired direction. Okay? When you have the case that the desired direction, of course, is this linear form, g of t equals a of t. So that's for that particular case. And what's interesting is to draw the graph of this function to see the effect that this particular factor k over I has. Okay? It's very interesting. It turns out what happens is that the system basically oversteers by that factor, just say by a factor of this constant a divided by square root of I. So if you wanted to minimize the error, to minimize this deviation so that the system doesn't have to overcorrect too much, so to minimize the error, you want that k to be relatively large compared to the moment inertia. What I'm going to do is I'm going to show you a graph. I've drawn a graph of this function and changed the value of k divided by I just to show you how the oversteering is affected by the value of that ratio of k over I. Okay. So I'm going to bring in the graph now. Zoom out just a little bit. And you can see what happens when you draw that function. Here's the time axis from 0 out to 10, unit 10, could be seconds. Here's the deviation, that e of t function that we just produced by solving by Laplace transform. And what you see is the green curve here in the middle, the very slight wiggle. That is when that ratio, k to I, is 16. If you decrease that value, you'll get the red curve here. Larger corrections are needed. And then if the ratio, if k and I are relatively the same, huge corrections have to be made to keep it on course. So again, that ratio is key to controlling the oversteering that's needed. But the solution and this effect was all possible by using Laplace transforms.